This video will cover the three acid-base theories that encompass all of organic chemistry. The first and most restrictive acid-base theory is the Arrhenius theory. The second is the Bronsted-Lowry theory. And the third and broadest definition is the Lewis theory. Another way to say this is that all Arrhenius acids are Bronsted-Lowry acids, and all Bronsted-Lowry acids are Lewis acids, but not the reverse, and the same for bases. Let's look at each of these theories in slightly more detail. The Arrhenius definition of an acid is a substance that dissociates in water to give hydronium ion H3O+. So for example, sulfuric acid dissociates in water to produce hydronium ion and HSO4-. The Arrhenius definition of a base is a substance that dissociates in water to give hydroxide ion. So for example, sodium hydroxide dissociates to give sodium ion and hydroxide ion. The Bronsted-Lowry definition is slightly less specific. A Bronsted-Lowry acid is a species that donates a proton, and so this includes all of the previous Arrhenius acids, like H2SO4, which dissociates to produce a proton and HSO4-. The Bronsted-Lowry definition of a base is any species that can accept a proton. So again, this includes all Arrhenius bases like sodium hydroxide, which can accept a proton from a strong acid such as hydrochloric acid to produce sodium chloride and water. This definition includes other bases that aren't Arrhenius bases such as ammonia, which can accept a proton from a strong acid such as sulfuric acid to produce ammonium ion and HSO4-. Remember from general chemistry that we measure the acidity of a solution both in the Arrhenius method and the Bronsted-Lowry method by the pH, which is equal to the negative log of the hydronium ion concentration. And this is measured on a scale from 0 at most acidic to 14, which is most basic. Also remember that the strength of an acid is measured by its acid dissociation constant, or Ka. The Ka is the dissociation constant or the equilibrium constant for the dissociation of the acid in water. This general reaction shows a general acid HA dissociating in water to give hydronium ion and the conjugate base, A-. HA and A- are known as a conjugate acid-base pair, and Ka is the equilibrium constant for this reaction. Remember that an equilibrium constant is products over reactants, and we leave out water, which is the solvent in this case. So a larger Ka value indicates a stronger acid, because a larger value means that this reaction lies further towards the right. The strength of a base, conversely, is described by the base dissociation constant, or Kb. So it's an equilibrium constant for the following reaction. It shows the base reacting with water to give hydroxide ion and the conjugate acid. Again, we have a conjugate acid-base pair here. And Kb is the equilibrium constant for this reaction. So products over reactants. And again, a larger Kb value means this reaction lies further to the right and that we have a stronger base. Ka and Kb of a conjugate acid-base pair are related. Ka times Kb is equal to the water ion product constant, Kw, which is equal to 10 to the minus 14th. You can actually just derive this equation from the two equilibrium expressions for Ka and Kb. And so Ka times Kb is always equal to 10 to the minus 14th when Ka and Kb are for a conjugate acid-base pair. Another way to express that is that the pKa and the pKb of a conjugate acid-base pair sum together to give us 14. So pKa plus pKb of a conjugate acid-base pair is equal to 14. What that means is that as the Ka increases, or the strength of an acid increases, the Kb of its conjugate base, or the strength of its conjugate base, always decreases, and vice versa. That means if we have a stronger acid, we have a weaker conjugate base, and vice versa. A weaker acid means we have a stronger conjugate base. And this is important because acid-base equilibria favor the formation of the weaker acid and the weaker base pair. And so if we can determine which is the weaker and which is the stronger of each, we can determine in which direction the equilibrium lies. The final acid-base theory we'll be considering is Lewis acid-base theory. The Lewis definitions include the previous acid-bases that we've already discussed and include some new ones that don't involve proton transfer. Lewis acid is a substance that can accept an electron pair. It's called an electrophile. It comes from the Greek, where electro is for electrons, and phile means lover of. So an electrophile is a lover of electrons. It accepts an electron pair. A Lewis base, on the other hand, is a substance that donates electron pair, and we call it a nucleophile, a lover of a nucleus, because it donates that electron pair to the nucleus of another atom. So this acid-base theory applies to acids and bases we've already looked at. For example, hydrochloric acid and water as our base. In other words, hydrochloric acid as our electrophile and water as our nucleophile. And our nucleophile can donate an electron pair to our electrophile to form a new bond. But this theory broadens the idea of acids and bases to compounds we haven't considered before, such as ammonia and boron trifluoride. Ammonia is our base, or our nucleophile, and boron trifluoride is our acid, or our electrophile. From now on, I'll be using abbreviations for nucleophile and electrophile since we use them so much. I abbreviate nucleophile using NU and electrophile using a capital E. And our Lewis base or nucleophile can donate a pair of electrons to our Lewis acid or our electrophile to form a new bond. Remember that our electrophile, boron trifluoride, is electron deficient. It only has 6 electrons around the boron center, and so it can accept that extra pair of electrons from our nucleophile to form this new bond. Another example of a Lewis acid or an electrophile is aluminum trichloride, which you'll notice also has an incomplete octet and therefore can accept a pair of electrons from a nucleophile to form a new bond. From now on, when we talk about acids and bases, we will mean the Bronsted-Lowry definitions of acids and bases. And when we mean Lewis acids and bases, we will use the terms electrophile and nucleophile to help us differentiate between these two types of reactivity. Pretty much all organic reactions either are Bronsted-Lowry or Lewis acid-base reactions. Many of the reactions we'll talk about involve nucleophiles and electrophiles, and we develop a system to keep track of the movement of the electron pairs of Lewis acids and bases using arrows. So for example, the reaction we discussed earlier between ammonium and boron trifluoride can be illustrated using arrows to show the flow of electrons from the nucleophile to the electrophile. So what we do is we draw the arrow starting at the electron pair of the nucleophile and going to the electron deficient center of the electrophile. And in this way, we show where the electrons are flowing and where the new bond is forming between the nitrogen of our nucleophile and the boron of our electrophile. It's the use of these arrows that makes up what we call a mechanism, a reaction mechanism that shows the flow of electrons to show what chemistry is happening. So it's really important for you to understand how we draw these arrows. The direction is always from the nucleophile to the electrophile. What this means is we're always drawing the arrow from the negative charge or the partial negative charge to the positive charge or the partial positive charge. Oftentimes the negative or partial negative will be a lone pair of electrons. Sometimes it will be a multiple bond or a single bond. And the positive or the partial positive is often an electron deficient center. This is a really important concept for organic chemistry, and I'd strongly suggest that you spend some time practicing drawing these mechanistic arrows.